Imagine an eye, not a human eye, a golden mirror, hexagonal tiles big as a house. This eye isn't looking at you or me, it's staring back in time across billions of light years to the very dawn of the universe. This is the James Webb Space Telescope, JWST, humanity's most powerful time machine. It doesn't see the universe the way we do, it sees in infrared, the light of heat. Infrared lets it peer through cosmic dust and through cosmic gas, revealing hidden nurseries where stars and planets are born. On Christmas Day 2021, a thunderous Ariane 5 rocket tore through the sky, carrying this precious cargo into the black of space. JWST traveled 1 million miles to the second Lagrange point L2. There it orbits the Sun in lockstep with Earth. Before JWST could show us the universe, it had to perform a breathtakingly complex dance of unfolding, 1 million miles from any helping hand. There were 344 single points of failure, 344 things that had to go exactly right. The first major hurdle was deploying the Sun Shield, a structure the size of a tennis court, made of 5 layers of captain, each thinner than a human hair. This delicate shield had to be unfurled, separated, and pulled taut by a system of motors, cables, and pulleys. After the Sun Shield was in place, it was time for the mirror. 2 side wings, each holding 3 mirror segments, had to swing into place and latch perfectly. Each of the 18 individual segments had to be adjusted by motors with nanometer precision, aligning them to work together as a single, flawless surface. Initially, the first test images showed 18 separate, blurry stars. But over weeks of painstaking adjustments, those 18 points of light slowly converged. That single image was a promise fulfilled. The eye was open. The wait was over. Now, the real journey could begin. Scientists had theories, of course. They expected to find small, clumpy, irregular protogalaxies, the cosmic seeds of today's grand spirals. But the universe, as it often does, had a surprise waiting for us. When JWST turned its golden eye to the deepest, darkest patches of sky, it found objects that shouldn't exist yet. These galaxies were named things like Glass Z12, Maisie's Galaxy, and they were not the faint, messy blobs we predicted. They were stunningly bright, massive, and well-formed at a time when the universe was just a toddler, only 300 to 500 million years old. The prevailing Lambda CDM model says bottom-up formation. Small dark matter halos merge over eons, pull in gas, and slowly build larger galaxies. Yet these ancient massive galaxies break that timeline. This is a fundamental puzzle. It forces us back to the drawing board to rethink dawn-of-time physics. It wasn't just the galaxies that were surprisingly mature. Hiding in their centers were monsters, supermassive black holes. These are objects with the mass of millions of suns or even billions of suns, crushed into a point of infinite density. A black hole grows by swallowing matter, gas, dust, stars. There's a physical limit to how fast it can feed, the Eddington limit. JWST found evidence of supermassive black holes powering brilliant quasars when the universe was less than 1 billion years old. One theory, direct collapse black holes. In the dense, chaotic early universe, enormous clouds of primordial gas could have collapsed directly into a massive black hole, skipping the star phase. JWST's findings are transforming black holes from cosmic oddities into central players in cosmic evolution. They may have actively shaped their host galaxies from the start. When you find evidence that challenges your most fundamental models, you don't just throw the models away, you get excited. This is where science truly happens. The discoveries from JWST aren't just footnotes in our cosmic textbook, they are forcing us to rewrite the entire first chapter. The early massive galaxies and black holes suggest that formation and growth in the universe's infancy were far more explosive and accelerated than predicted. Maybe the nature of dark matter, the invisible scaffolding upon which galaxies are built, is more complex than we thought. It's reminiscent of the moment when observations of Mercury's orbit couldn't be explained by Newton's laws, paving the way for Einstein's general relativity. The data from JWST is that beautiful, stubborn fact that won't fit into our existing boxes. It is telling us that the universe is more creative, more complex, and more surprising than our theories had allowed. These revelations have ignited a vibrant, healthy, and absolutely essential debate within the scientific community. On one side, you have cosmologists who argue that these early JWST findings might not require us to tear up the old textbooks just yet. This isn't a fight, it's the scientific method in action. It's a beautiful process of thesis, antithesis, and synthesis. Through more observation, more modeling, and vigorous debate, a new, more complete understanding will emerge: the synthesis. So what should you, the curious citizen of the cosmos, make of all this? You should revel in it. This is what discovery looks like. It's messy, it's contentious, and it's exhilarating. While JWST is a powerful time machine for looking at the distant past, it's also a revolutionary tool for exploring worlds much closer to home, the exoplanets orbiting other stars. By analyzing which wavelengths of light are absorbed, JWST can identify the chemical fingerprints of the gases present. JWST has studied the atmospheres of so-called hot Jupiters, finding not just water vapor but also clear evidence of clouds made of silicates. It has detected sulfur dioxide on one world, suggesting active photochemistry, where the star's light is driving chemical reactions in the planet's sky. But the ultimate goal is to study smaller, rocky, Earth-sized planets that orbit within their star's habitable zone, the Goldilocks region where temperatures are just right for liquid water. The detection of a biosignature, a combination of gases like oxygen, methane, and water vapor that is difficult to explain without the presence of life, would be one of the most profound discoveries in human history. Every major astronomical discovery has forced us to reconsider our own significance. We once thought we were the center of the universe. Then Hubble showed us our sun was just one star among hundreds of billions. And that galaxy was itself just one among hundreds of billions. This progression has been called the principle of mediocrity, the idea that we are not special, that our situation is likely very common. JWST, however, is adding a fascinating new wrinkle to this story. It shows a universe ripe with potential for life, and also how specific and precarious our path to existence has been. We are the products of 13.8 billion years of cosmic evolution, now able to piece together the story. Look up not with arrogance nor with insignificance but with wonder and gratitude. And that in itself is anything but mediocre. For all the incredible discoveries JWST has already delivered, it's crucial to remember one thing: we are just getting started. The data we've seen so far is just the opening act of a grand cosmic play. The biggest questions remain, and JWST is our best tool for tackling them. One of the biggest is the nature of dark matter and dark energy. Together they make up 95% of the universe, and we have almost no idea what they are. Then there are the first lights. The ultimate goal, the very first generation of stars, the legendary population 3 stars, is still on the table. The telescope is more than a machine, it is a legacy. It is a testament to what we can achieve when we dare to ask big questions and work together across generations to answer them. The journey into the unknown is far from over. In fact, it has only just begun.